Thank you in advance for watching this video. My name is Andrew Schilf, and this is my Physics 2211 Lab 1 on constant velocity. So just a little bit of an introduction. The purpose for this lab was to observe the motion of an object moving at the same speed without changing direction, or constant velocity. And we want to compare the observed position of this motion to the predicted position that we will obtain from a computational model. So the system in this experiment will be the expo marker that I will be rolling, and the surroundings will be everything else, like the floor. The aids I'll use in this lab is GlowScript for the computational model and the tracker app for the observation model. So this lab goes with the Newton's second law, otherwise known as the momentum principle. And as you can see in this picture, I derived the formula F net equals change momentum over change in time to equal the velocity update formula. And the reason why this relates to our lab is because we are showing when the net force is zero, the final velocity equals initial velocity, which in turn means constant velocity throughout the entire duration of the experiment. So the procedures for this lab are simple. First, we'll want to obtain the observed position through a live experiment. Second, we'll want to obtain the computational position through GlowScript. And third, we'll want to create a spreadsheet to compare both the models from 1 and 2. So let's get into it. For the observed position, first you'll want to film the video, as you can see right here.
Go ahead.
Roll the marker for a meter, that's the expo marker. Second, you'll want to upload the video into the tracker app, and you'll want to calibrate the video. So as you can see, I had the meter stick in the background, and I set the meter to equal a meter in the tracker app so that we can then go in and track the position frame by frame. And I had a video, here it is, that shows all the frames that I took to track the position of the marker. And third, the data that it pulls from the app, you put it into a spreadsheet. You can either do Google Sheets, Excel, or any other app. I did Excel for this. And using that data, we will want to obtain the initial velocity and position. So as you can see, at time zero, my position was 0.043 meters. And I got my initial velocity as an average velocity. So I just took the position from time zero to time 0.1, and I got my initial velocity to be 0.84 meters per second. So using this information, we can go into GlowScript and do our computational setup. So as you can see here, I inserted my initial position and initial velocity, and I changed my delta t to be 1 over 30 because my video was shot in 30 frames per second. Moving on to the code, more code. I used the velocity update and position update formula to predict the final look. And as you can see, this is the momentum principle here. And then position update formula uses that velocity we got times the delta t. Now that we did both, we can put them on a graph together, and here's what it looks like. So as you can see, the orange line is my predicted motion from GlowScript, and the blue line is what actually happened when I rolled the marker. So just a little debrief, my marker did not keep constant velocity. As you can see, it slowed down a little bit, and we'll discuss why that could be uh, in the further slides. So potential sources of error, because as you can see, it didn't keep constant velocity. The two main obvious ones are friction and air resistance. These are going to be forces going against the marker, slowing it down. Another one I came up with was not 100% accurate calibration. The tracker app was a little buggy, and the system could have like not calibrated 100% correctly, leading to different distances calculated. And just, yeah, position tracking just went over that as well. So we come to the question, what if we were to flip the x-axis? Well, if you take 1.2, move it to the left, you take 0, move it to the right, your slope's just going to become negative. It's going to be the same line, same slope, it'll just be in the negative direction. And is the net force really 0? Well, the computational model overpredicted the final position. So like real life systems like friction and air resistance were involved, pushing it in the negative x direction, meaning the net force was not really zero in the x direction, but the net force in the y direction is zero. Otherwise, it would just be flying into space. But yeah, that's it. Thank you for watching.